Okay, hi everyone. Thank you for joining us for our second PyData virtual meetup. We're delighted to have you here with us on this Friday night. For those who are joining us for the first time, welcome to the PyData KL fam. So you may ask, what is PyData? PyData provides a forum for the international community of users and developers of data and analysis tools to share ideas and learn from each other. We are a bunch of individuals with different experiences and background coming together to share our knowledge and learn from each other. So let's get connected to the community by joining us on our Discord group. So this is our QR code and you can scan to join us on the Discord group. Yeah, I'll just leave it here for a moment for you guys to scan it to join the group. Okay, that's all for the introduction. So let's move on to why we are here today. So today we have Ryan Sim to share with us about not so simple linear regression. Ryan is a first-year PhD student in the Singapore University of Technology and Design. His primary research interests are in algorithm game theory, dynamical system, and social choice theory. Before I pass the time to Ryan, if you have any question to ask, feel free to ask in this pigeonhole. You may scan the QR code or you may just go to the website pigeonhole.at and enter the passcode, or the link will be shared in the chat box. Yeah, so if you have any question, feel free to ask it there and your question will be answered at the end of the sharing session. So that's all for me for now. Let's pass the time to Ryan.
Hello, can you guys hear me?
Yes, can hear you.
Okay. Oh, I'm seeing someone in the chat saying that there's no volume, there's no sound. It might be you might have to check your like computer audio settings or something, because I think for everyone else it's working. Yeah. Okay. Cool. So hi guys. My name is Ryan with two N's for some reason. As mentioned by Carmen, thanks Carmen for the introduction. I am a first-year PhD in SUTD, and I'm here to talk about linear regression. And you might be wondering, why do we even need to talk about linear regression? It's it's so simple. In fact, you may or may not have even used it before. But I think for those of us who are in the data analytics field, we tend to sort of push aside the linear things, the simple things, and focus on more complex models, like, for example, machine learning models, deep learning models. I guess the purpose of my presentation today is really to sort of convince you guys that linear regression, although it is relatively simple, so my title is actually a lie, it can still be useful in many contexts, and it's important to actually study it in depth. So first of all, a bit of a disclaimer here. I'm not much of a data scientist myself. As you've seen from the introduction, I focus more on theory, and I'm particularly interested in statistical theory, which is why you'll see some bits and pieces of that in this presentation. But I'm not going to go too much into the math, right? I'm going to focus more on practicality and how you're going to be able to use this stuff in your daily lives. So if I can, okay, cool. So these are the things I'm going to go through. First of all, obviously an introduction, some preliminaries, and then I'm going to present on simple linear regression, which is a very basic model that I'm sure you guys have seen before. And if you haven't, great. If you have, then I think a lot of this stuff is at least good to revise, and hopefully I can give you guys some new insights. Prediction and uncertainty, this is something that will be very useful in practice. Some elements of model selection, and I'm going to end off with some extensions to the linear regression model. Okay, So why do we study statistics? Why do we need to study statistics? Because at the end of the day, linear regression is really a model that it exemplifies statistical learning, right? And I think this diagram sort of helps to illustrate why this is important. Because in the real world, which is what all data scientists are trying to predict and to try to understand, there are these unknowns, right, that exist. And what we can get from the real world, what the world can give us, is just data. And with data, we can pass it to the left-hand side, to the theoretical world, via learning, and generate these models that can, it's almost like a loop. You use data to get models, use models to predict unknowns that exist in the real world. And these models can take many forms, right? Like, for example, logical representation is a theorem, for example, or a formula. A model could be something more complex, like a regression model, could be something like even a black box, machine learning model. And yeah, so I guess this is sort of the general, simple idea behind statistical learning. And of course, the question becomes, why do we want to study linear regression? Well, there are a few reasons. I'm going to go through them very quickly. So obviously, the elephant in the room is that although linear regression is well established historically, it's sort of been overtaken in terms of performance by these flashier models, right? Like comparing a Tesla to a Proton Saga. But just like the Proton Saga, you can still use it. And one of the reasons is that, firstly, you can have many sort of useful methods of regression, because regression is not just linear regression. There's a lot of kinds of regression that I'll briefly touch upon. And these are sort of extensions of linear regression which can be used. There's also many ideas behind better methods. So things like cross-validation, regularization, all these things can be illustrated using linear models and then extended to complex models. And it's also easy to explain and understand the parameters of a linear model. So, things like if you're working in a company, a lot of times stakeholders would like to, they like seeing numbers, right? They like seeing the fact that you have some very nice formula that describes the data in a nice way. And it's also very easy to visualize. And finally, linear regression is part of the shared culture of data analysis, so we should definitely appreciate it. This is more, obviously, it's not, you're not going to use this to justify using linear regression to solve some crazy problem, but it's good to know. Right. So we're going to start with simple linear regression. And before we go into what linear regression is, let's talk about regression itself. Like, what does the word even mean, right? Well, the name doesn't sound as good. It's like regressing, going backwards, but it somewhat is, right? You're going backwards. You're using the data. So if you look at the white box here in the center, given what we know about the x values, which are sort of the independent variables, the covariates is what we call them, what's our best guess for y? And y is a dependent variable. So you can think about this like x is kind of your data, your training data, and y is the dependent variable that you want to arrive at. Okay, and yeah, so regression is really all about estimating some kind of function. So you're not estimating the values themselves. You're estimating a function that gives you the correct values or the best guess for the values. And we'll talk a bit about prediction later on, but predictions, when you use that function R and you feed in new information, new observations, and you get a new estimate for Y. And yeah, don't bother too much about all the technical stuff like what's IID. That just means that it's like all your samples are from the same sort of distribution, and this fancy E here is just the expectation. So you'd expect that your final regression function gives you a good guess for Y. Okay. Yeah. So this is sort of key to. I mean, literally is the formula. So you have this formula, very nice here. Y equals beta naught plus beta 1 x plus epsilon. So I'm going to go through this one by one. Y is it's essentially the thing you're trying to get, your data point, your answer, and x is the data points that you get that so you can think of it like if you're plotting it on a xy plane, you have this point which is like, I don't know, 140, gives you this value which is 10. So you're going to sub 140 in, you get 10. And I mean, I'm sure we all remember from secondary school or primary school the y equals mx plus c formula, and this is obviously reminiscent of that. So you can sort of transfer that idea over. So in this case, beta naught will be your c or your y-intercept, and beta 1 is your slope. Or your gradient. And these two are sort of the key parameters. So this is a very important word, parameters of linear regression model. And then there's just this little thing here, this epsilon. What is this epsilon? And the epsilon is unfortunately something that, they didn't tell us about in secondary school. Everything is perfect. Everything is a nice linear line. But in real life, that's not the case, right? Especially in, with less linear data sets. You will have error, right? Because what you're doing is you're saying, here are all these red points. We're going to just plot a straight line through it, screw it, just have a straight line through it, and there's going to be errors. So all these like sort of thin blue lines that are perpendicular to they're parallel to the y-axis are essentially measuring the distance of your fitted line from the actual data value. And the idea behind regression really is to minimize the sum of all these values. So don't bother too much about all these things. It's just sort of technical details. When you have a hat over something, it just means that that's an estimate, right, from the data. And what's important is these last two, the residual and the residual sum of squares, or some will call it error or whatever. But the error is basically you take the actual data value, the actual value of the data you want to predict, and you minus the predicted value using your straight line, and you get the error. And then you take the sum of the squares of all these errors, because if you have positive and negative error, you don't want that, right? You want error to be like a strictly positive or strictly non-negative thing. So that's your residual sum of squares. You just take the sum of all this, and this is the total square errors made by your linear model. And yeah, so this is a nice sort of way of checking to see if your model is bad. Obviously, the value of it by itself doesn't really mean anything specifically. It could be in the billions and still be a good model, or it could be nearly zero and still be a bad model. It depends on your data and your values. But what's one nice thing about linear regression that you don't get in more complex models is this. And when I say nice, I don't mean the equation in the center of your screen, because that doesn't look very nice at all. But the point of this is saying that, you have your beta naught and beta 1. There is a formula that you can just plug in. Literally, you can just take the data points and generate these values, the covariance and the variance, and you just plug it in. And you always get an unbiased estimator for the best fitted line. So what does that mean? It means that you always get a good fitted, not always a good fitted line, but you can, by using these values of beta naught and beta 1, you can get the best possible fitted line that is unbiased. And by unbiased, I mean in the statistical sense, which means that you're not consistently predicting higher, consistently predicting lower. You're sort of not biased to any side of the data. And so that's a very powerful thing, and something that you don't really see in many other sort of statistical models, right? There's really not many. For those of you who have studied more complex machine learning models, a lot of times how you arrive at these parameters is really through a very extensive hyperparameter search or something like that. But here you can just plug these values in and you've got it, right, essentially. And that's really nice. But let's look at an example of this in practice, right? Because one thing that my prof always told me is that you can, all this is very nice, but you actually use it might not be that useful. So here's an example. So this is data from the 2000 US presidential election, which was Al Gore versus George Bush. And in Florida, I think the name of the place was Palm Beach in Florida. Bush won only by 537 votes out of 6 million cast. Sorry, this is for the whole state of Florida. And there were a lot of critics. So obviously 537 out of 6 million is tiny. And critics claim, critics, obviously people who didn't support George Bush, claim that in Palm Beach, which is a town in Florida, a lot of votes went to this guy called Buchanan, Pat Buchanan, instead of Al Gore, due to the ballot design. So this is what the ballot looks like on the right-hand side of your screen. If you want to vote for Al Gore, who is the second on the left column, so to speak, you would have to punch out the third hole. And obviously, voters are like, some of them could be very old, some of them could have, eyesight problems. So they will see, oh, Republican first, Democratic second. So I'm just going to punch out the second hole. And this kind of confusing ballot design ended up with a lot of votes going to Buchanan instead, or at least that's our hypothesis, right? So we're going to have to check this hypothesis. And what would you say is a decent sort of model? I mean, you already know the answer because that's what this talk is about, but it would be fairly, fairly common. It would make a lot of sense, right? That there's a linear relationship between one person's votes and another, right? Because you want, in general, like in an area, if there's more people in an area, there would be more votes for one person, for person A over person B. And in a place that's less people, you would expect similar ratio, but with obviously less values, and that means that there is, or at least you hope that there is a kind of linear relationship between these two people. So let's take a look at. Sorry, yeah, I'm going to share my other screen. I don't know if you guys can see. Can you guys see? Yeah, so I'm finally going to go into Python here because this is PyData after all. But again, all the code for this, it's pretty simple. So, yep, can see, okay. Yeah, all the code for this is pretty simple, and there's a lot of resources that you can find online. So this is just to give you guys an idea of how the workflow should be, right? So you start off with obviously reading your data. I'm using pandas here. And this is just a scatter plot of the data. So between Bush and Buchanan. So what we're postulating here, what we're hypothesizing, is that Bush and Buchanan have a linear relationship, right? And you expect Buchanan to have a certain amount of votes given the amount of votes that Bush has. Okay, and so on the x-axis we have, I forgot to plot the. Anyways, on the x-axis this is Bush, and on the y-axis this is Buchanan. And so there's two pretty big outliers here. I think you can tell immediately. And I want you guys to guess. Obviously, this is not in person, so it's a bit hard to respond. But like, what do you think this value is? Which place do you think this is? And if you guess Palm Beach, I gave you like half a second to answer. But if you guess Palm Beach, then you'll be right, because that is Palm Beach. And what you can do is actually fit a linear regression. So it's just using the sklearn module, just fit x and y. So in this case, x is Bush, y is Buchanan, and blah blah blah. You get a pretty bad R squared value. I'm not going to go into too much about like what R squared is really, but because I don't trust it that much, there are better methods to score your linear models. But this value is not good, right? You want it to be close to 1. And 0.4 is not good, and you can clearly see why, right? There's these two pretty big outliers, and up here I checked where Buchanan had the most votes, and it's actually precisely in Palm Beach. So this value is Palm Beach. This is the fitted line, the red line, and clearly, just by the eye test, there's a problem here. There's a very big problem here. So let's go to. Okay, yeah. So there's a very big problem here, and in fact, if you plot out a few things. Right. So these are the 4 things that I plotted. So this is Palm Beach. The second plot is the residuals. So if you remember, the residuals are the errors, and you can see that the errors go from range from like around -300 to like 300, right? Based on this line. But if you plot something else, so what I'm saying is you have this nice formula here, right? That's done by your Python. It just gives you a fitted line. This thing, Buchanan equals 0.0049 times Bush plus 45.29. This is your beta 1, this is your beta 0. But what if we tried something else? What if we use a different sort of formula, right? And there's nothing wrong with that, actually, because really, if you think about it, what you're doing is you're modifying just the values of the data, right? And in the context of votes, right, voting, where you have a lot of people voting at once, you can think about it, like from high school mathematics, we learn what logarithm, what adding a log does is it sort of like compresses things in your space, right, of your real numbers. And so what that means is that errors aren't as, like outliers aren't as big of an influence. And so let's try. So what I did in the code, which I probably need to share now. I'm sorry for coming back here, but yeah. So if we change it to log x and log y, exactly the same thing, just fit again and run, you get something that looks a lot nicer actually. So this is Palm Beach, the one on the top, and it doesn't seem that bad, right? And if you look at the residuals, it actually only stretches up to 1 and like minus 0.8. So this seems to be a lot better, right? And so this brings up a few problems, which I'm gonna talk about now. So the first thing is that we know, first of all, that Palm Beach, well, we don't know for sure, but we can guess by the eye test that Palm Beach in this context, in the first experiment, is pretty far out of reach. That means essentially Buchanan's getting way too many votes. But if you look at the second plot, it looks like Buchanan's actually closer into the line. So then the question becomes, how do we make sure, right? Because I'm sure you guys have seen this perhaps in your daily work, in your school projects, but how can you confidently tell your stakeholders that yes, Palm Beach is too high? Why not this one at the bottom? Like the very bottom vote. And that's where we go into prediction and uncertainty, and this is something that is obviously very important because a lot of what we do as data people doing data science is that you need to predict certain things, and you need to tell people with conviction that what you're doing is correct. Okay. And also, I forgot to mention, there's another issue here, which is which one do you choose, right? So you have this very simple model, you have a slightly less simple model, but they both work. They're both linear regression models, essentially. So then the question becomes, they're both simple linear regression models. Which one do you choose? And that's the topic for, the third part. So this is the second part. I'm just going to go through this first. Okay. Yes, I think I see yeah, okay. I think I'm going to go through the prediction part first before going to a break. Is that okay? Or would you guys like a break now? I'm not really sure how to. Oh, yeah, actually you can vote in the chat, I guess. There's like a yes, no button. If you all prefer to take a break now, just yes. And if you want to break later, just no. Oh no, it's tied. Okay. It's 2 to 3. Oh, it's 1 to... Okay, nice. That means I can continue. Great. Then I'll finish this part first before going on. Okay, so prediction. Prediction is, something that's, as I mentioned before, near and dear to machine learners and statisticians alike. And generally the idea is, given some function or given your data, you want to get a function out of it. That's your first step. That's your training. And then the second step is, given a new observation, you use that function that you've just established to generate a new data point, right? Your new y value. So previously we assumed that there was a linear relationship with the variables, right? Because if you remember this, the initial plot of the data points, the scatter points, looks pretty much linear except for these two, right? So we've assumed the linear relationship, and we've used our fitted line to guess what the y value should be given some x value. And as I mentioned before, the key question is, how good is this prediction? And so we go again to a very not so nice looking equation. But generally, again, without bothering too much about what all this means on top, what the theorem means, is what we're saying is that you can generate something called prediction interval. And some of you might be thinking, oh, what's the difference between that and a confidence interval? I'll talk about that very briefly later on. But a prediction interval is generally a set where you can say with alpha probability, right? So an alpha size prediction interval, a 1 minus alpha prediction interval is a place where you can say with alpha probability, y star will be inside the interval. So your predicted variable, your predicted value will be inside that interval. And again, one can easily implement this in code, or even better, there's a lot of libraries, sklearn included, that have already implemented it. You just need to call the function. Okay, so the prediction interval is different from a confidence interval in the sense that it takes into account the data scatter, in the sense that you are sampling, right? You're sampling from all your available data points to generate a new data point, and this sampling creates a sampling error, right? So I'm not going to go too much into the technical details here, but just know that a prediction interval is generally wider than a confidence interval. Okay, and so with the election data, we are pretty sure about the straight up, the straight up linear regression, the basic one without the logarithm. We're pretty sure that Palm Beach is way out of order there. So let's try with the logarithmic one. And after doing it, after writing some code in Python, which maybe I can show you now. I mean, it's pretty basic stuff. You can just basically get your data from the linear regression thing itself, the fitter model, and then plot it out. And you can see it's pretty interesting because all the points that we thought, oh, it could be out of, it could be an outlier, actually all pretty much lie within the prediction interval, right? Within these green dotted lines. And you can see here specifically, the prediction interval is between 5.2 to 7.6 approximately. And the actual value of Palm Beach is 8.15. So even in a sort of more squished version of the data, right? Like because you've logarithmized, you've taken the log of both x and y, even then it's still our prediction interval. So you can say with 95% confidence, because I ran this prediction interval for alpha equals to 10%. Okay, sorry, with alpha equals 5%. You can say with 95% confidence that Buchanan is getting way too many votes compared in Palm Beach compared to everywhere else. And so, you can go back to your, I mean, this is actually what they did. This is literally what they did when the election results came out, and they wrote a paper about it, and they said, Buchanan got too many votes because of this ballot design. And then from then on, every election after that, they changed the ballot design, right? So even a simple model like this can be used to affect big things, essentially, is what I'm trying to get at. Okay, I think we're going to take a bit of a break here before we go into model selection. So yeah, feel free to ask any questions on the pigeonhole or to get a drink or a snack or something. And yeah, pass back time to Carmen.
Okay, hi guys. You may ask your question here. If you have any question, please ask it here, and we'll answer your question at the end of the sharing session. Thank you. Our session will resume in 5 minutes. We'll start in approximately 8:40. Yeah. And if you want to join our Discord group, you may join our group here, or ask your questions here. Do remember to ask your questions here if you have any, and we'll answer it at the end of the session. Okay, I'll pass the time back to Ryan.
Thanks. Okay. I hope everyone had a good break to refresh your mind. And now we're going to go into something maybe a bit more difficult because it's a bit more, it's a bit more nebulous. It's a bit harder to quantify which model you want to choose. And that's what model selection really is all about. Previously, we talked about prediction intervals, right? Basically, having a nice way of saying this model or this data point that I'm trying to predict is outside of the prediction interval. Therefore, it's an outlier, and you can cut it from. I mean, not cut it from data set, but you can say that with certainty, that that data point is a mistake or something of that sort. But there's also the issue of, do you use this kind of linear model? Do you transform it? All these things are sort of encompassed by the idea of model selection. And in fact, to start, I'm going to present on something a bit more complex, and that's multiple linear regression. As the name suggests, multiple linear regression is literally just regression, but with multiple covariates, right? So you have one y and many different x's, right? x1, x2, x3, x4, or up to, x however many. But the one important thing is that all of these are sort of linearly attached to the formula. So you can just imagine, if we had the y equals to beta naught plus beta 1x plus beta 2x2 plus beta 3, so on. You can just keep extending it. And this is the example that I'm using, which is a data set. I think it's available online. I mean, it's definitely available online, but basically you want to predict how far the mileage of a certain car is given these four variables. The question is, can we just, dump all of this into a linear model? Or do we need to be more selective? You might be wondering what's the problem with dumping all these in, and I'll go into that a bit later. But first, I'm going to give you guys a few examples of the importance for model selection, right? And to motivate this issue. And it's actually still a big issue, right? Like it's something that's quite up in the air. So the first example is crime rates. So this is a data set that I think has been taken off the internet actually since this survey was done, or this research was done, because I mean, it's crime data, so you don't want people to go around misusing it. But essentially, this was trying to predict whether or not not whether or not, but predict how much crime would occur in an area, depending on all these different covariates. So they looked at the data of each person and the number of crimes that they did, and they tried to predict it using things like age, whether or not they're in a southern state, this is in the US, education, expenditure, and so on. And all these numbers on the columns on the right essentially represent, the first one is the covariate, the expected, the what do you call it, estimated value. Then the second one is the standard error, and then it's t-value and p-value, which I'm not going to talk about much here. But generally, the question becomes, you have so many different covariates, so should we eliminate variables from the model? And if so, how do you choose, right? So the p-value on the right is really talking about the significance, the statistical significance of the different covariates. And if you maybe go read online, some of them will tell you to just take the ones with like stars. So in this case, it'll be like expenditure, age, intercept, which is basically a beta knot, and unemployment, 25 to 39, and you can just ignore the rest. I'm here to tell you that that's not exactly true. Don't trust just the p-value too much. There's a very good mathematical reason behind it, and generally the reason is that the higher the value, or the absolute value of the beta value, so the higher the absolute value of the coefficient itself, the more likely it is to have a higher p-value. And so this could skew the data pretty extensively. I mean the p-value pretty extensively. So later on, I'll give you some ideas that can help you to remove certain covariates whenever necessary. But that's one thing, right? That's one issue, removing certain covariates. But there's also the other issue, which is causality. And I'm not going to go too much into causality here, but the question becomes, do all these things really cause crime to happen, right? I mean, I don't want to say this is a mathematical issue. This could be more of I guess, a philosophical issue, but there is mathematics behind it, right? There's a mathematics of causality, which I'm not going to go into too much here because it's very, it's like a lot of logic and a lot of theory. But another thing that you need to watch out for in practice. So just to go back, the causality thing, you can sort of use your common sense, right? If something seems to be causal just empirically, then you can leave it in. But the second thing to watch out for is multicollinearity, and what this is really just what do you call it? Correlations between different covariates. So if you remember, covariates are essentially meant to be independent variables, right? They're all meant to affect your y variable, what you're trying to predict. But if you have multicollinearity, what happens is that you might have correlation between two covariates. So if you look here, expenditures is 3-star. I mean, just in terms of the R output, this just means that it's very important. So you're like, okay, let me add expenditure in. But then something else that's here is age. But age sort of depends on expenditure, don't you think? Like, I mean, and they both affect each other to some extent. And things like education, how much education you have would affect your expenditure. Whether or not you're unemployed affects your expenditure, your wealth affects your expenditure. So all these things are affecting each other. And this is what we call multicollinearity. So if you want a very nice way to sort of take a look just in a visual way of these issues, you can actually use something called a correlation plot. I don't have one right now, although maybe I'll talk about it later, because there's a very nice website that shows these ideas in a visual way. But yeah, a correlation plot can be done just in a few lines in Python. So you can just do that. And if things have high correlation, then probably don't put both of them in the model. And so that's for simple linear models, essentially. But then you have more complex models, right? Like ALPHAGO, which is obviously a very complex system and a very complex model. And there's so many factors to consider, right? You have things like the number of neurons in each layer, what activation function to be used by each layer, all these things like batch size, learning rate, exit criteria, so many things, right? And the question becomes, how do you even begin to narrow it down? Because you have literally an infinite number of models to test, right? You can't just say, I'm going to try out every single combination, because that would take an exponential amount of time and most likely would result in the heat death of the universe before you're even halfway through. So how are you going to do that? You're probably going to have to do something called model selection. I mean, not probably, you are going to have to use model selection. And previously, we measured how well a model can fit the data, right? That's what we had with our least squares approach, and that's what we saw with our prediction intervals. But we want now to be able to measure a model's ability to generalize. Okay, and this is where sort of the key comes in, because if you have a simple model, you're going to have something called underfitting. And this is something I'm sure you guys are probably familiar with, but it just means that, if you extend, you're going to have high bias and you're probably going to have high error. But you can probably bring this model to a different, or like you can sample from your data set and that same model would still work. But if you are using a very complex model, let's say a linear model with like 10,000 covariates, and if your training set, you train it all on say 50% of the data, if you try and predict, it's probably not going to give you a very good result, because what's happened is that it has overfitted to your training data, right? And what you're trying to do is to essentially find a middle ground between this, right? A simple model is maybe too simple, a complex model is too complex. I don't know why I said that line, that literally added nothing, but something that could be useful to think about is Occam's razor, which is very nice logical statement made in like way back when. And essentially it just means the simplest explanation is usually the correct one. But I think in the age of data science, the the most middle explanation is usually the correct one, right? You don't want it to be too simple, you don't want it to be too complex, you want it to be just nice. These are some of the common sort of model selection scores and methods out there. You have, Akai-K and Bayesian information criterion. You have things like K for cross-validation, forward and backward stepwise regression. And this is specifically for regression, by the way. So obviously for other models, you have different methods. But something that I want to talk about, because it's so ubiquitous to the data science space, is LASSO. And just a side note that most of these can be implemented very easily in whatever you use to do your data analytics, right? You can just, most statistical modules allow you to just run a function and get a score. And then how you choose based on that score is really up to you. And you can obviously choose to implement like 100 different scores and just choose the one that's the best scoring. You can use an ensemble method or whatever. But something that is very nice is LASSO. So I'm just going to talk a bit about the concept behind LASSO. LASSO stands for least absolute shrinkage and selection operator, and essentially what that means is that you're penalizing complexity. So remember we talked about the least sum of squares, the residual sum of squares, right? That's the error up here. And what we're doing is we're just adding a new term to the back of this error, right? And we're saying that you're trying to minimize this error, yes, but there's also something else that you need to minimize. And that's essentially how big the coefficients are. And so what that means is that if you have 10,000 covariates and you take the sum of all these, let's say all your coefficients are like 1, right? Then you're going to have an extra 10,000 here. And assuming your lambda is 1, you have an extra 10,000 here. And so the minimum, in the computer might be like, oh, maybe that's too high. So I need to turn some of these to 0, right? And that's essentially what LASSO does. It takes, all your covariates and it chooses the ones that are most important and it turns some of them to 0. Okay. And lambda is just a parameter that is called regularization parameter. That word is horrible, but it just states how harshly you want to penalize, right? So let's say you want really, really harsh, right? You only want to choose maybe 2 or 3 covariates. You just set it to like 100 or something. And we'll see some examples of this later on. Well, later on, I mean now actually. Give me 1 second. I'm going to go back to the code. See if I can. Okay. Yep. Okay, so LASSO. This is with the data set with the car mileage. And this is our regression model. By the way, this is with stats models. So if you want to do like more general machine learning stuff, then you probably use scikit-learn. But stats models is pretty nice as well because it gives you sort of everything just in one line. And yeah, so these are the coefficients, these 5 here. You can see like 188, and they're all non-zero, right? So essentially what they're saying is that, just to remind you guys, this was the car mileage example we had previously where you had 4 things and you're trying to predict 1. So these are the 5 total coefficients. And you can see that, all of these are being used and your R-squared is pretty high, it's like 0.88, whatever. But let's say, for example, you want to figure out, let's say you really need at most 3 coefficients, right? You want 3 covariates. You're trying to eliminate the last one. So what you can do is you can run LASSO, as you can see here. And I'm just doing a grid search here. You don't actually need to do this. You can just do like LASSO and fit accordingly. And you can get, with alpha equals 1, you get something like this. The coefficient values are here. And you notice that these are all still actually non-zero, which simply just means that you're not penalizing enough. So let's try up it to 10. And you can see here that the third one, so x3, which I believe is I can't remember what exactly the data thing actually means, like whether it's I think it's the weight of the car, yeah. So this is 0, which means that LASSO has said, all right, I've had enough of UX3, and it's like, you're not going to be using the model from now on. So all this is fitted. The R-squared, as you can see, it has dropped. It's now 0.79. But you have narrowed your model down to only 3 covariates. Obviously, this is a very sort of flippant example, right? Because there's only 4 covariates. But if you can think about it in the context of more complex models, that this could be useful. Okay, and this is a simple plot of the paths, which can also be done pretty easily in Python. But essentially, what this means is telling you when the different coefficients leave, right? Leave the model. So x3 is here, I think x1 here, x2 is here, and x4 leaves here. And yeah, so as I mentioned before, alpha equals 10 results is something like this, and you're essentially saying that x3 is not needed in a more simple model if you're trying to simplify it. Okay. Yeah, so I mean, that's all I have for LASSO. If you guys have any questions, feel free to put them in the pigeonhole. But generally, the idea with model selection is, as I mentioned before, you want to sort of have a way of narrowing down your huge sort of set of possible models. And all these methods that I've mentioned here. Actually, maybe I can talk a bit about cross-validation, because do I have time? Okay, I don't have much time. Yeah, I don't have much time. So all these things, can be found in online and in very sort of nice textbooks that I'll recommend at the end of the talk. So a few extensions. So obviously, for those of you who have done linear regression before, you've probably already seen all these things. But I think what's really cool about regression is that it extends very nicely to other things. So you have logistic regression, which essentially is just linear regression, but you're doing it for categorical data points, right? So you're trying to classify stuff. There's also a really, really interesting thing called generalized linear models, GLM, which does not assume that a response variable is normally distributed. So distributions are a huge thing in statistics. I'm not going to go too much into it, but if anyone's interested, you can go read up on something called exponential families, which is a very very, very technical thing. But it's really interesting because you can essentially apply regression to things that you will not expect to be able to apply linear regression to, just by removing the assumption that your y value, your response variable, is normally distributed. Okay, and the error term that we saw, right, the one where you take y minus y hat, and you square it, blah, 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 that can be generalized as a loss function. And for those of you who do machine learning, you've probably already heard this many, many times, but you're always trying to find a good loss function. And simply put, in linear regression, the loss function is just the residual sum of squares. And regularization, the idea that we talked about at the end there with LASSO, is often used in modern machine learning. It's often used in optimization problems, in more sort of theoretical context, and it's a very, very powerful tool. And just like a little tidbit for you guys who are interested about interpretability or explainability. So there's this thing called LIME, which stands for Local Interpretable Model Agnostic. Okay, I forgot what the last word is. What agnostic? Yeah, anyways, essentially what it is is a methodology whereby you can go about sort of applying these linear methods to machine learning models such that you can better understand what the model is doing. Because as we all know, a lot of machine learning models are black box, right? You put in some data, it spits something out, and you're like, okay, what does this mean? How did you arrive at this? And what interpretability studies is essentially this some way of getting into that black box and trying to understand it. So I've actually linked a lot of these in the notebook itself. So just to share some of them. So seeing theory is what I was talking about with the okay, I forgot what I was going to say. The correlation plot, yes, precisely. So it tells, it's very nice. Those of you who are familiar with Iris dataset, you know exactly what's happening here. But essentially, all these things are pretty cool stuff that you can go and check out if you wish. So this is really great, right? So and I'm pretty sure the code is for this, they present it somewhere in a paper or something, and it's also pretty easy to code it out yourself. There's some stuff with prediction intervals here from Stanford. There's a very nice handbook about linear regression. I'm not going to open all of these links. There's also I had a logistic regression example, and this is a post by the guy who actually wrote the Python Lime library. If you want to use it for your machine learning stuff. And these are a few of the books that I've read. I mean, I haven't read the first one in full, but I've heard it's pretty good. Truth About Linear Regression. All Statistics is like one of my favorite books because it's really kind of easy. It sucks you in with a lot of intuition. There's not too many theorems and crazy stuff. It's not too mathematical, so I find it quite fun. And I think this one is a bit more complex and a bit more like involved if you're interested in the elements of statistical learning by Hasty, Tipshirani, and Friedman. And yeah, there's also this online book which I've been enjoying. Pretty interesting, Interpretable Machine Learning. It's free for all, obviously, as you can see, and it's online. So yeah, so these are just a few sort of things that might be interesting to you guys. And let me just go back to And just to conclude, right? So all we've talked, we've run the gambit essentially of linear regression ideas. We've talked about the basics of linear regression and how it can be applied in your practical purposes or just for learning, right? And so some final tips to using regression in practice. The first is knowing when and where to use regression. Obviously, you can't just dump this anywhere on a crazy model. You might want to focus on choosing when and where to use it. If you can see, by common sense, you can plot it out graphically and see if your data is somewhat linear, and then you can just apply it. Try to gain intuition from the mathematics behind regression and why it works in practice. This is not because I'm a math student and I like people to study math, but mostly because it's useful to see, right, behind the veil of what a loss function does. Why does regularization work? And speaking of regularization, my God, that word is just horrible. You should use model selection techniques when you're designing models to improve performance, right? Don't just guess at the parameters and submit that one, right? Just iterate, use grid search, use cross validation, use LASSO, all these things. And finally, I mean, maybe I should put this earlier, further up, but use graphical methods to get a feel for your data before you even start applying regression. And yeah, I mean, I think that's all I have. Any questions? I think the questions are probably on the... okay. Okay, when should we not choose linear regression? Okay, so there's a few... Okay, I just saw a second question, and that was an interesting question because I had that question as well when I was learning this. Okay, so when should we not use linear regression? But obviously, if your data doesn't seem to be linear, I know it's a kind of dumb answer, but that's how it is, right? Like the first thing that I normally think about is, does it make sense for it to be a linear sort of relation? Because you have to remember there's only one thing you're trying to predict, right? There's only one response variable, and you could have however many covariates. And I think the key is trying to understand the data itself before you even start choosing your model, right? And I mentioned graphical methods. That doesn't always work because if you have a very high dimensional data set, it might be hard to even understand graphically what the data means. But try and think of, because whenever you get data, you're getting it with respect to some kind of real world, some kind of real world observation, right? You're getting real world data. So try and understand if all these make sense. Like the example with the cars, the passenger car mileage, you have things like the volume of the car, the horsepower, the top speed, the weight. All these, you can conceivably, with common sense, imagine that they affect the mileage, right? So I would say that that's when you should start using linear regression. And when you should not choose linear regression is when you have these really complex models, especially things like, I mean, just as an example, like obviously, you for things like, for example, like computer vision related stuff, you're not obviously not going to use linear regression, but for very, very high dimensional data sets, you might want to actually go to use the second thing, which someone mentioned, which is PCA, which is principal component analysis, when you are sort of choosing which model to use at the end. Because PCA is, for those of you who are unaware, is essentially a way of reducing the dimensionality of your data, right? So you have like I don't know, 100,000 covariates, and you can use PCA to sort of narrow it down however much you want. And as this anonymous person mentioned, you can use it in combination with regularization. I think in my experience, it's useful sometimes. I honestly can't say much because I haven't been in the industry for very long. I've only done some internships. I don't know how useful it is in the industry specifically, but I do know that in theory it is valid to be used sort of in collaboration with regularization. So yeah, I mean, you should definitely experiment and read more textbooks, I guess. I mean, that's one. I mean, experiment with stuff, read stuff online, and try and apply this to sort of your everyday sort of data science work, and see if you can get better results by using PCA. I think generally, from my experience, PCA is useful if you're trying to visualize things, and if you're trying to sort of get a better understanding of the dimensionality of the data, if that makes sense. And I forgot what the thing is, but you can plot PCA in a very nice way. There's a module that I've seen. Okay, I don't want to go in Google now, but if you're interested, you can go and check this out. But yeah, I'm pretty sure that visualizing PCA is actually a very nice way of narrowing things down. So yeah, I would agree that it's good in combination. Yeah, hopefully that answers the question.
Would you want to share your screen to explain further?
I mean, sure, I guess. Yeah, the example I was talking about is, wait. Okay. So this is PCA. I don't go too much into this, but this is from the Python Data Science Handbook, which you guys should read. It's a good book. It's another recommendation. Yeah. So what PCA does is essentially sort of narrows down the number of components of the data. So one really cool thing that you can actually use it for is noise reduction in your data set. And I don't know how many you guys do CV, but computer vision, but noise reduction is obviously a really interesting problem to have. And I can't really remember how PCA works specifically. Yeah, because I mean I didn't study that much, but let's see if I can figure it out just by looking at the code. Nope, it's just using the module. So yeah, sklearn is great. It does PCA for you. You don't actually need to know how it works, although it'd be good to know how it works. So yeah, just go and read it, I guess. But yeah, so what you can do is like if there's noise, like so this you're trying to read the numbers with your code and there's noise, you can actually use PCA to reduce the dimensionality such that the noise is reduced, and therefore you can select the useful features from them, right? So this, I think this paragraph is the key. So rather than training a classifier on high dimensional data, you can actually train it on a PC8 data set first. So you lower dimension it first. You lower the dimensionality first, and then you train it. And I think that, first of all, is good for computational speed, obviously. And it's generally, I think, it obviously depends on your data set, but it could be helpful to sort of get your regularizer more, get more value out of it, if that makes sense. I don't know how well this works in practice, but I think in theory it sounds like a good idea. Yeah.
Yeah, I guess there's no other questions. Do you guys have any question? You can unmute yourself and ask if you have any question.
So PCA is SVD. Okay, sorry, yeah. So as Atam said in the chat, thanks for that. Yeah, so PCA actually uses SVD. That's really cool actually, because I mean I learned SVD, but I didn't learn PCA specifically. So yeah, it's good to know that there's a link there between the nonsense that I'm learning and actually useful stuff. So yeah, so SVD stands for singular value decomposition. Essentially, what you're doing is you're studying the eigenvalues of your matrix, which in this case is your data set. And what you're doing is you are trying, I would guess, what PCA does is that it sort of reduces your, what do you call it? It takes the eigenspace and it finds the ones with the highest spectral radius. So if you guys aren't familiar with what I'm talking about, then you don't really need to worry about it. Essentially, what you're doing is you're choosing the most effective, the things, the columns of the matrix that affect your eigenspace the most, if that makes sense. So yeah, so PCA, that's what it does, I guess. Thanks, Atham.
Okay, are there any more questions? You can unmute yourself and ask if you have any question. If not, then this could be this. Then yeah, this is the end of the session, and yeah, we are on Discord. You can join this Discord group to join the Pi Data group. We are on Discord. The group is there where everyone share their interests and knowledge and learn from each other there.